Hello, guys. First of all, I'd like to remind that last time we were introducing the Lenz law, which tells us in which direction the induced electric current, because of change of the magnetic field flux, will flow. So we figure out that the direction will be defined in that way, that the magnetic field created by the induced electric current will be directed will oppose the change of the magnetic field flux, which causes this induced electric current. Means that the system, according to the conservation of law of energy, would always tend to oppose any changes of magnetic field flux through the chosen current loop. So based on that, we also considered and introduced the concept of induced electric field, which is related and defined also by both the Faraday's law and Lenz law. And today we will continue with considering some example for calculating induced electric field, in particular by a solenoid, like some long solenoid, which for which we will consider two locations. One will be outside, like outer space of solenoid, and inter space of solenoid. So we'll try to find the strength of the induced electric field by alternating current with certain frequency flowing through the solenoid. Afterward, we will proceed further with some practical applications of combination of Faraday's and Lenz law, and in particular focus on AC and DC electric generators, like alternating current and direct current electric generators, and finish our today's lecture with the consideration of circular currents, which can be induced in continuous pieces of metals, which are moving, like entering and going out from the constant magnetic field. So let us start. I will change to the different camera. Okay, 1 second. Need to find also our PowerPoint presentation, since we will need some slides from there a bit later. Okay, good. So now we start with an example for calculating induced electric field by alternating current flowing through a solenoid. So let us consider a solenoid. We have some solenoid, and there is some electric current as a function of time, which is flowing through the solenoid. So the radius of this solenoid is R capital, and this function which defines the time dependence of electric current is the following. It will be I maximum, so amplitude value times cosinus omega t. Okay. So this is the system which we consider some long solenoid with electric current flowing through it, alternating electric current flowing through it, and this is the function which defines electric current as a function of time. The radius of solenoid is R capital, and now let us consider the case when we want to calculate induced electric field by such solenoid in the outer space. So we will have at radius R some loop, and here at this distance, which is radius R, from the center of the solenoid, we want to calculate the induced electric field. And this R is larger than radius of the solenoid. Okay, so in order to proceed further, we definitely need to recall the Faraday's law in general form, which we considered during last lecture. So this linear integral over a closed path of the scalar product of electric field vector times ds vector is equal to minus d magnetic field flux over dt. So we keep this in mind, and now we first need to define, okay, what will be this derivative. So, and we are looking for electric field as a function of radius r, like induced electric field. So this derivative will be the following. Here is this magnetic field flux derivative over time is equal to minus d over dt. And here we consider b times pi times r squared. So just a few comments why we consider this magnetic field flux. So we know from previous lectures that because of the structure of solenoid, we have very strong magnetic field in the interior area of solenoid, and the outer space, in the outer space of solenoid, a magnetic field is much weaker. So we can, for simplicity, neglect with the magnetic field, weak magnetic field in the outer space, and that's why the total magnetic field flux through this dashed loop shown on our image with radius r larger than the radius of the solenoid will be just a product of a constant interior magnetic field of the solenoid times cross section of the solenoid, because everything what is outside the solenoid, this area outside the solenoid, their magnetic field will be very weak, and we can neglect with this. So keeping this in mind and factoring out constants from this derivative, we will end up with such equation. Will be pi times r squared times d b over dt. So this is this will be the derivative of magnetic field, like magnetic field change over time inside the solenoid. So also we know that magnetic field in the interior part of solenoid is equal to mu naught times n. This is number of coils per unit length times I, or electric current which flows through this solenoid. And taking into account this function, which we got at the beginning of the as a condition for our case, we can substitute this I with its time-dependent function. So this will be mu naught times n times I maximum times cosinus omega t. So now we need to determine this derivative, like the rate of changing of magnetic field flux. It will be minus d b over dt is equal to minus pi times r squared times constants in this equation, which are these three terms, mu naught times n times I maximum, and here will be d cosinus omega t over dt. So let us go to another slide and rewrite this equation. So it will be d f b over dt equal to minus pi r squared. Let me check again. Mu naught n. Okay. Mu naught n I maximum d cosinus omega t dt. So the derivative of this cosinus omega t will be minus sinus omega t times omega, the derivative of the argument of this cosine, which will be just omega, and that's why minus and minus will cancel out. We will get some positive value, will be pi times r squared times mu naught times n I maximum times omega and sinus omega t. So now we are done with the right side of this Faraday's equation, and we need to deal with the left side. On the left side, we have this integral, linear integral over closed path, and assuming the symmetry of this long solenoid, like of the induced electric field created by a long solenoid, when the length of the solenoid is much larger than the radius of the solenoid, we can consider in this circular symmetry that within this circular path, which we choose with radius r larger than radius of the solenoid, constant induced electric field, and its integral over closed path, like closed circle, will be just product of the magnitude of this induced electric field and circumference of this circle, which will be 2 pi times r. And according to Faraday's law, this will be equal to dFb over dt, and this is equal to pi r square mu naught times n I maximum omega sinus omega t. Okay, from here we can easily express induced electric field as a function of r, and that will be mu naught times n times I maximum times omega r square divided by 2r n times sinus omega t. So this is our final equation, which satisfies the condition when r is larger than the radius of so when we calculate this induced electric field out in the outer space of the solenoid. So when r is larger than radius of the solenoid. And from here we see one thing. Actually, would be reasonable to highlight two things. First of all, this induced electric field is changing as a function like sinus omega t, as opposite to electric current, which is flowing through the solenoid and governed by cosinus omega t. And second, that electric field is reversely proportional to 1 over r. So it reduces in magnitude while we going further from the solenoid. Okay, so this is the first part of this case when we consider r larger than radius of the solenoid. Now let us consider the other part when we have radius smaller than the radius of the solenoid. That means that we will try to calculate electric field in the interior area of the solenoid. So for this purpose, we again need to write down this derivative df b over dt. And in this case, it will be a bit different. So since we, let's maybe show it here, have some solenoid, and our loop, which we consider, now has radius smaller than the radius of the solenoid. In this case, for calculating magnetic field, we need to consider only cross area of this smaller of this loop, which we consider. And this area will be smaller than the area of the cross section of this solenoid. That's why we need to consider, instead of pi times r square, which we considered in the first case, we will now use area pi times r square, the radius, where r is radius of the loop which we want to calculate. So that will be, maybe I just delete this. We don't need it further. So this will be minus d over dt, product of constant magnetic field in the interior part of the solenoid, times pi r squared. And this will be minus pi r squared, since these are constants, times dB over dt. Good, so now we again need to take this derivative, so it will be dfb over dt is equal to minus pi r squared mu naught ni maximum d d cosinus omega t over dt. And again, we have derivative equal to minus sinus omega t times omega. As a result, we get pi r squared mu naught n times I maximum times omega sinus omega t. And according to Faraday's law, this should be also equal to E times 2 pi, and here is this radius of the loop, which is smaller than the radius of the solenoid. So from here, we again can express induced electric field as a function of radius, but this time it will be actually different, since we have R here, so we cancel out this second power and cancel out this R. So eventually we get mu naught times n times I maximum times omega divided by 2. This everything is multiplied by R and sinus omega t. So in this case, we also see that electric field is changing as a function of sinus omega t. However, as opposite to the previous case, when we considered the outer space of the solenoid, inside the solenoid, induced electric field increases with increasing radius. So it actually reaches its maximum value at the radius of the cross section of the solenoid. Okay, so with this we are done, and now we proceed further to the consideration some practical applications of Faraday's and Lenz laws. And one of the standard, very broad and important application is electrical generation, electrical generator. So there are many different types of electrical generators. However, we can summarize them in two categories. So it's alternating current AC generator and DC direct current generator. So these devices are used in order to convert mechanical work into electrical energy, which is definitely very important for our modern society and lifestyle, since all our supplies and gadgets, some climate control, everything is requires a lot of electric power, and this need increases over time quite dramatically. So let me change the screen. So initially, we will consider AC generator. So we see here that we have some current loop, which is this frame in the constant magnetic field created by this permanent magnet. So of course, it's the most simple configuration. So could be that this magnetic field is created by electromagnets. So you need to run first some current to create magnetic field, and then this generator starts to work as a generator. So it kind of has self-supporting process of operation when part of generated current is used for electromagnets to create magnetic field. However, in this case, it's already based on permanent magnets, and taking into account that nowadays there are very many really high quality permanent magnets which create very strong magnetic field, like beyond 1 Tesla, which is really amazing for some small neodymium magnets available on the market. There are really many solutions for electrical generators based on permanent magnets, because they became very small and strong. So then we have some frame which can spin here in this around its axis, and obviously while spinning with respect, like in this uniform magnetic field, there will be time-dependent magnetic field flux through this frame. So we will just consider it in a second in more details. And then each of the like ends, let's call it terminals of this frame, connected to its ring, like current collecting ring. And then there are some contacts from these current collecting rings to external electric circuit, which where some loads and consumers can be hooked up. So the current, or here is showing some time dependence of electromotive force, looks like some sinusoidal. So we have a period. So period can be calculated as a time interval between points with the same phase. So we can go from 0 to some time when this phase is repeated. So when we have 2 maximum or just the condition for the same phase is already sufficient enough to determine the period of this oscillation, with this current or voltage signal. And we have half period, some positive values of electromotive force, and some half of the period, this generator produces negative values for the induced electromotive force. Similar dependence will be also for the induced electric current. So this type of signal, when we have half period positive and half period negative, voltage or current, these signals are called alternating currents. So they can be not necessarily only sinusoidal, could be also some square signal, other forms, but sinusoidal, assuming the nature of the construction of most generators, is one of the most common and widely spread alternating current. And in particular, in our electric power grid, we have sinusoidal signal and with a maximum voltage of 220 volts when we operate with a single phase with respect to ground. And the frequency of such signal, which is 1/t, the period of the signal for European countries and also in particular in Kazakhstan, is 50 hertz. In United States, for instance, this voltage, amplitude voltage is twice smaller, like 110 volts, and frequency is higher. It is operating at 60 hertz. So there are some minor differences in power systems in different continents. However, other from that, they are quite similar and operate based on the same principles. So let us come back to our slide where we can write something. So in such a system, when we have a frame rotating in a constant magnetic field flux can be represented as the product of like constant magnetic field, like uniform magnetic field and constant, times area of this frame times cosinus theta. And this theta can be represented as some time function with this angular frequency, product of angular frequency and time. So this can be written as b times a times cosinus omega t, assuming that at t equals 0, theta is equal 0. So we don't have some constant phase to add. Then this electromotive, induced electromotive force is calculated based on the Faraday's law, where is negative of the rate of changing magnetic field times number of coils in this frame. dFV over dt. And taking into account expression for the magnetic flux, we will have minus n times a times b times d cosinus omega t over dt. And as a result, we get for the electromotive force, induced electromotive force, n times a times b times omega sinus omega t. So the amplitude value of induced electromotive force, E, oh, sorry, not E, but epsilon maximum will be N times A times B times omega. And this will be reached when the frame with respect to the magnetic field is oriented at angle of 90 degrees or 270 degrees. So as I mentioned, industrial frequency most commonly accepted in the world is either 50 hertz or 60 hertz. So this is all about alternating current generators. However, we also have another class of generators, and they are direct current generators. So here we see the schematic of a direct current generator, and it is very similar to the AC generator. However, this instead of using for each of the terminal of this metal like conducting frame, its own current collecting ring, some special device which is called commutator, formed by two isolated halves of current collecting ring, is used. And in this case, when we change the polarity in, for instance, induced electromotive force, we also change the sides of this commutator, which are connected to positive or negative terminals in a given half period of time. And that's why we never get negative parts of the half time, because we have initial connection, we have positive electromotive force, which is changing also by sinusoidal, but until reaching its minimum value, and instead of going down like normal signal from AC generator, this because of the presence of this commutator, the polarity, negative polarity, is kind of flipped over because of touching different terminals of the rotating frame. And we again get positive signal generated by such DC generator. So DC means that we don't change the direction of electromotive force and direction of electric current. So in this case, it always positive. So it not constant. It's we get some pulses of voltage and current. However, they always are in the same direction, and that's why we can already call this current DC current. Obviously, that it's not always what we want. So usually we prefer to have some straight line, and like DC and constant, not only constant in the direction, but also constant in magnitude, voltage and current. And for this purpose, there are different approaches. So first of all, we can make a much more complicated system of frames and commutators. So we can use many metal frames and many commutators, and then they will smooth this pulsed DC signal. Another option, when we connect in parallel to this output of the generator some capacitor, and that will also help by charging and discharging this capacitor. It will help to smooth these pulses for the generated DC current. So these are approaches for making more smooth pulse DC current, and at some point when it's really necessary, by combining different technical solutions, it is possible to make really constant value for generated voltage and current by these direct current generators. So next practical application, in general, it's some effect which is caused by Faraday's law, is called eddy or circulating currents. And let me show you. So this effect is based on generating some circulating currents in continuous metal plates or some metal conductors when they moving in and moving out from constant magnetic field. So what happens? So if we know that we can in a closed conductive loop induce some electromotive force and induce some current. So here happens very similar picture. We have just some continuous metal plate, and we create some loops of electric current while magnetic field flux through these plates is changing. And if it goes from outside where we don't have magnetic field, it moves inside in the magnetic field. Obviously, magnetic field flux increases, and the induced this circulating current, which is called eddy current, is directed in that way that the generated magnetic field by this eddy current is opposing the change of the magnetic field flux. Means that eddy current will always result in attenuation, like breaking, like slowing down the motion of this metal plate in the external magnetic field. So in this case, we see that when it moves from outside into magnetic field, so it moves from left to the right, this magnetic force will be kind of repelling it outside from the area with magnetic field. It means we'll slow down its velocity, reduce its velocity. And also when it already moves out from the magnetic field, it also causes changes of magnetic field flux from maximum to some minimum when it's already outside. This magnetic field also tends to reduce its velocity in order to get as minimum rate of changing magnetic field as possible. And this effect is usually considered as some bad effect because we lose energy for generating this unnecessary, in many cases, eddy currents, and just convert electric energy to heat and warm up our metal constructions. And in order to fight with this, the easiest approach is to divide some continuous pieces of metal plates into small parts which are isolated from each other. So in that case, we prevent forming large current loops, this circulating current loops, and that allows to get smaller magnetic force acting on these moving parts, and that's why with smaller current circulating current loops there will be less dissipating of energy by heating these moving metal plates. Not necessarily that they should be always moving, they could be also stationary, but stay in changing magnetic field, not constant. For instance, maybe you have seen previously, there's transformators which can convert signals alternating current with different voltages. So we either can increase voltage of alternating signal or decrease voltage, depends on the construction of this generator. We will study this in details a bit further. So they use some ferromagnetic core for operation, and this ferromagnetic core is always made from plates of iron, which are isolated from each other by some glue and just stick to form some continuous structure, but made of plates isolated from each other. So that is made in order to prevent forming large radius eddy currents, like the circulating currents, and prevents from excessive loss of energy by heating this ferromagnetic conductive core of the transformator. However, these devices, this effect also has some practical application, and as I mentioned, if we have some moving part, some moving conducting plate inside the magnetic field, the effect is that magnetic field, magnetic force slows down the motion of this plate. So this is widely used in some breaking down the fast movement of like fast spinning systems, when we have, for instance, some wheel of like train wheels. They are made of continuous metal disc, which is spinning with quite high angular velocity. And if we run some current through electromagnets located next to this conducting metal wheel, then generated eddy currents will result in attenuation, like slowing down this motion. And another possible application of eddy currents is in the counter of electric power, or like old-fashioned counter of electric power, when we have two coils and current in one coil is proportional to the voltage in the network, and current in the other coil is proportional to the current which is consumed by the network where this counter of electric power is connected. So both of them create some alternating magnetic field, which generates eddy currents in aluminum disc. So this aluminum disc starts to spin because of some magnetic force acting on it, and this aluminum disc is connected to some mechanism which counts the revolutions of the disc, which is proportional to the electric power consumed in the network. Since electric power is a product of electric current magnitude and voltage, since there are two electromagnets responsible for each of these parameter. Their common effect on the spinning conditions of this disk result in calculating the total power consumed within the network. So even some negative parasitic effects sometimes find practical applications. So I think that today we are already running out of time, and we finished all topics which were planned to be considered at our lecture. So please don't forget that on Saturday, means tomorrow, you will have a second midterm, so prepare yourself, and I hope to see you on Monday, when we will proceed further with our course. Thank you very much for attention. Have a good day. Bye-bye.